So it's still morning. Good morning. Welcome to this presentation. I think already Professor Schroeder began with a good introduction in the morning about this terrain analysis of watersheds or the terrain to derive this flood risk information. So I will continue, or I will contribute to this discussion with a case study that I performed during my master's thesis. My name is Egerton University. So we've seen already that floods are the most common as well as the most destructive, and also due to land use change and climate change, there is also an increase in the frequency, of course, the occurrence and situations of risk. And we've already seen that people interfere with these interception rates, this timing and the magnitude of floods as well continue to increase. And we can use this type of an assessment. It's a tentative risk assessment, but it can be used for various purposes. We can, of course, inform what are suitable land use decisions for a particular area. We can also give this information to insurance companies, and they can determine, for example, this area is more susceptible, then of course maybe higher premiums and so on. And we can also come up with response strategies in the case of disaster. So already it's been shown this type of a relationship. So I have also this example here. So this is an idealized hydrograph, and we see, for example, where you have this type of a peak discharge, you may expect to have small basin areas, high drainage densities, very steep slopes, as well as very steep channels, and also where you have this equidimensional basins, so more circular, meaning water accumulates almost at the same time. So we have this type of relationship, and this was already described. So generally speaking, in geomorphometry, we look at the geometry. So for example, the basin area, the topography, what is the relief of this basin, and the gradient of the channel, and also the shape of the earth, so also the basin. And we use these parameters, and I'll classify them. These are already classified into three. So we have linear parameters. So for example, the stream order, the bifurcation ratio, basin perimeter and length. And these are used to provide insight into this important information, so discharge, permeability, and infiltration. So we also have aerial parameters, such as the basin area, drainage density, frequency, circularity ratio. These have also been used to provide have been used to infer information about the magnitudes of peak and mean runoff, as well as subsurface material permeability. I have an example here of a picture showing where we have high drainage density. It's most likely this underlying material is silty clay. Yeah? So where we have this low drainage density, then we have also a different type of soil. So many of this information that is useful for deriving this flood information is already implicit in most of these parameters. So finally, the relief parameters, which provide the three-dimensional aspect of these basins. So we have the slope, we can get the runoff direction and volume. So these parameters are the main factors that affect the shape of what we saw the hydrograph before. There is also the availability of digital elevation models, and there is now a global coverage by these models, meaning that for every part of the world, even for these data scarce regions, we can perform this type of an analysis and we can compare. And an example is also given by Professor Schroeder. And of course, we have many implemented algorithms. Also, an example was given of this flow direction algorithms, so single direction and multiple direction algorithms, and these are implemented, and so I chose to use QGIS as an example because these algorithms exist. So the general workflow is as shown here. So we have a DEM which gives us this elevation information. So we use the principle of steepest descent because we know water flows from high areas to low areas. We can calculate the direction of flow. And then we can also determine for each point how much how much area that is upslope of this point contributes drainage to this point. So we have the contributing area grid here. Then an important parameter is this channel initiation threshold. So there is a minimum amount of water or contributing area that is required to initiate and to sustain these stream networks. So this must be determined, and then we can extract our drainage network and the watersheds. So depending also on the choice of algorithm, sometimes it becomes necessary to redefine these streams so that they conform to a particular rule, as I will show an example here. And then we can then compute these parameters. These parameters depend on characteristics of the drainage network and the watershed. So for example, the number of streams, the length of the streams, the relief, and so on. So once we have this information, we can derive these parameters, and then we can classify them according to how we perceive or how we know they affect the rate of flow or how they contribute to flooding. And then we can derive finally a flood hazard map. Of course, there are a number of issues. So one has already been explained. We have different sources of DEMs. Secondly, how do we determine a suitable value that will allow us to determine where our streams begin so that we can have an accurate stream network? Of course, we also need to see are these streams well defined, so the accuracy of this information is also important. And also, it makes sense if we can automate some of these processes, because we need to extract these watersheds, because these parameters depend on these characteristics of both the stream networks as well as the watersheds. So now, can we automate this watersheds information? Because normally we make use of PowerPoints for each stream, and we can also automate this process, as I will show here. And also, because we can compute these parameters, so these parameters are quantifiable, but we can also quantify stream flow information. So this is already available. So is it possible to come up with a quantitative relationship between these two values? So in a sense, by addressing these issues, we want to improve the use of this terrain analysis for flood risk assessment. So I will give an example of the case study area which was done in this area in Germany. So the headwater streams of the Danube River. So to extract the stream network, I used a method called the stream drop analysis. So by stream drop, we take the difference in elevation between the beginning and the end of the stream. And this is an empirical property of properly graded stream, meaning they have reached a state of equilibrium between erosion and deposition. So what this method does, it takes a range of threshold values given in this first column here, and for each threshold value it computes a number of properties. Most important, this mean drop, so it will take all the first order streams, calculate the average drop for all these first order streams, and then also the mean order of all the higher order streams, and compare them in a t-test and try to find if there is quite a statistical difference between these two. So where there is very little statistical difference, we take this value. So we take a t-test value of the 95% confidence interval. So we need a t-test value of 2. So something that is close to 2. So it's absolute, so it can be negative or positive. So I'll show you some results. So when we extracted the stream network based on this stream drop analysis, so this is what we obtained. First of all, we classified the area generally into this type of landforms, and we see there are flat areas and these hill slope areas. So you notice there is a difference between our extracted streams and our reference streams down here. So for these hill slope areas, we see that we have a relatively low drainage density. For these flat areas, we have a higher drainage density. So there is this type of a mismatch between this information, and this can be explained as follows. So we consider that for these higher areas, because the terrain is well defined, then there is an issue. The threshold was not sufficient to capture all these stream networks. And for these flat areas, we know that, so these are the flat areas. So drainage normally is forced. So if the data is not variable enough to capture these small variations, then we have this type of a problem where the algorithms will force these drainage lines to appear. Alright, so the next thing is to what I talked about, redefining the streams. You notice here, for example, that these two diagrams here are geometrically the same. Now the difference comes because when I label each of these stream segments, you notice, for example, here 2, 2, 2, 2, 2 all over. Ideally, this is one stream, yeah. But for when we delineate it, so we get so many stream segments, and each of these stream segments begins at this intersection point. So we want to redefine that in such a way that we have one continuous stream segment, so that we have it only labeled once. So how do we achieve this? So there was an approach in QGIS that was used. So we take each computed stream order. So we take, for example, the stream order 1, 2, 3 separately. So they are split according to the order. And then within these individual orders, they are dissolved. So we have all order 1 streams dissolved. So for example, all these stream segments will be dissolved into one stream segment. So, but the problem with dissolving is that you create these multi-part features, meaning that these streams, all of them will be considered as one object. So you need to split this into individual objects. So meaning we want this order 2 streams separated from this. But also one problem that arrives is that at the point where two order 2 streams meet to join an order 3 stream, this is permanently dissolved, and we need to also split this. And so we introduce another variable here. So we introduce a higher order stream to split these 2 stream segments, and then we have our correctly ordered stream. So this process is described here. And then finally you can merge all these stream segments and you have your correctly defined streams. So the next thing is also how to generate these 4 points. So these are the points at the end of the stream, either the area of highest accumulation or the area of lowest elevation along the stream network. So we simply explain it as follows. You need to identify a point along the stream network that is of highest accumulation value. So this is most likely at the end of the stream, but we also consider that stream networks join, so we don't want this point to be at the intersection point, so about a pixel away from this intersection point. So this is what this algorithm does, and it's shown here. So when you have a series of points for all your stream segments, you want to have only one point at each stream segment. So you have this also select algorithm provided here. And then for each of these 4 points, we use this information to identify what is the area that contributes drainage to this particular point. So all the area that is upstream. And this is an example here. So we've also seen these parameters, and as I've said, they depend on characteristics of the stream network and the watersheds. So when you compute them, you get a lot of values. So for example, we know that area is given in meters squared. We have drainage density in kilometers per meter squared. So all these values are different and we cannot readily combine them. So we need to normalize them. This was already shown. So in a way, we can think of this as percentages. So we bring them to a common evaluation scale. So a ratio scale, yeah? So and this is what we have. So we can visualize each of these values individually based on how they affect the risk of floods. So this is a simple classification based on equal interval. So we notice, for example, here, this is the basin area. Smaller watersheds, of course, means higher risk according to our analysis. And also we have the circularity ratio, so more circular basins, higher risk as well. And then we combine all of this together, and then we derive our flood hazard maps as such. So this is what we were aiming at, but of course there are some issues that need to be addressed. So now the most important issue is this value that we apply to initiate our streams, because now the accuracy of these parameters depends on the accuracy of our stream network and watershed. So this value must be correct. And also, we can use various algorithms that account for this spatial variability in drainage density. We consider that for a very large area, this drainage density will vary between different places. In my example I showed, we have these flat areas and these hill slope areas, so drainage density varies between these regions. So for a very large area, it's worth considering that drainage density varies, and we need algorithms that can account for this. So the second thing is also to evaluate the different DEMs. This difference is systematic or random. An example is also given this morning. So this is already being addressed. And finally, we can also try and see whether there is a quantitative relationship between these parameters and this stream flow information. So because we can quantify both values, so we try and determine, for example, we can use multiple correlation and try to determine is there a quantitative relationship between these different values. So I mentioned that this was done in QGIS. We can also use the graphical modeler such as this to derive all these parameters. We can also add scripts if you so wish to provide some flexibility, and also where tools are not available. So this was done as part of my master's thesis, and I had as supervisors Professor Schroeder and Bear. And so thank you for your attention.
Thank you, Dennis, for your presentation. We have room for some questions.
Okay, please.
Yeah.
Thank you for your presentation, Dennis. I would like to know if you have tried to use your same model using QGIS, using ArcGIS.
So I mentioned this is adapted from what was available in ArcGIS, but of course there is a difference in the algorithms. I have not compared both individually, but this type of an approach has been used. And so I only provided my own workflow based on the available tools in QGIS.
Yeah. I have a question also prepared to Professor Schroeder. Actually, in all the presentation on flood risk management or flood forecasting, I did not see the contribution of remote sensing. Where do you see the potential use for remote sensing?
Big potential. So first, of course, remote sensing is there because the DTMs are based on.
That is fixed.
Yeah, okay.
That is,
second is, in this approach, just the terrain has been considered. But now, of course, there are other factors which are clearly affecting also the discharge. Land use, the coverage of inferior soil, and so on and so on. And this can be extracted, this has to be extracted from remote sensing. Yeah. So I think this model here is still not complete. This is just one part, the geomorphological part, but now other parts, land use, and so on, has to be added. And this surely has to be extracted from remote sensing data.
Thank you.
Can I also answer that? Because I have been thinking about the same. At the last part where we need to compare the relationship between these parameters and stream flow information, I think it might be useful to add information about the different land use types as well, so that we can determine for particular land use how much stream flow results, and also not just the terrain characteristics but also the actual land cover as well. So this can be used to improve this type of analysis.
Also for quality assessment of the models, actually. Yeah. Because when the flood comes, of course, the remote sensor you can clearly see where are the flooded area, inundated area. So for quality assessment, for sure you can also use it, but to improve the land use.
Yes, I think with flash floods there is a problem because these events are rather short in time. So it depends, of course, exactly you can acquire for this short time your image. Maybe then drones again will be better choice. Yeah, because we were short in time for flash floods at least.
Okay, then thank you for